Hey, chemistry students, this is Miss Ruark. This is Vodcast 8.5, where we're going to talk about colligative properties. So, what's a colligative property? Well, a colligative property is a property that deals with the number of particles that are dissolved in a given mass of solvent. So, we're looking at the number of particles that are dissolved, the number of particles of solute dissolved in a solvent. Okay. Physical properties of a solution can actually be different from the physical properties of the solvent after you've put in your solute. Okay, and you've seen this before when you put salt in your water to boil your spaghetti or your macaroni and cheese. Or if you've ever heard about up north, they salt the roads so that they don't ice. Okay? Or if you've ever made homemade ice cream and you put salt in your ice. Okay, so what are the ways that the solution can be different from the solvent? Well, the vapor pressure can actually be lowered. So vapor pressure lowering. We can elevate the boiling pressure or the boiling point, so boiling point elevation. And we can also depress or lower the freezing point, so freezing point depression. 3 different colligative properties that we're going to look at in this vodcast. All right, colligative properties are properties of a solution that depend on the amount or number of solute particles that are dissolved in solution. Okay, that's the second time you've seen that. You're going to see it more, so don't forget it's all about the number of particles. For colligative properties, the identity is not important. So size and molar mass don't matter. It's how many of the particles did you put in there. That's what's important. All right, when we do colligative properties, we're going to use molality to calculate our colligative properties, not molarity. Little m, not big M. And remember that molality, this is why I made you learn it, is moles of solute per kilograms of solvent. Okay, that's why I made you learn it, because we need to use it here. Okay, so how can we change these properties? Well, vapor pressure lowering. Remember that vapor pressure, okay, here's our container with water in it, and here's my water molecules. They're all happy and content floating around in solution. Well, not in solution, in water. Okay, so these water molecules, sometimes they want to escape and change into gas molecules, right? And the gas molecules that sit above that liquid, that's your vapor pressure. So it's that's your vapor. And the pressure that you feel that comes off them is the pressure exerted by that vapor, and it's in dynamic equilibrium with its liquid in a closed system. So what does it mean by dynamic equilibrium? Well, that means that as one goes out, one comes in. So it's a constant rate of evaporation and condensation going on at the same time. Okay, so they're both the same process, just going in different directions, and it's happening at the same time. So dynamic equilibrium. All right, when a solute is added to a pure substance or a pure solvent, the vapor pressure is going to be lowered. Okay, well, how is the vapor pressure going to be lowered? Okay, this is where you might, where on your notes it says sketch this. Okay, so how will it be lowered? Well, we've got our water here, and then I'm going to stick in some, let's say we put in some salt. Okay, so the salt is the red, and we're going to throw in some salt particles, and they're just kind of chilling in here too. Okay, and when we put in these salt particles or salt molecules, they're going to dissociate and break up, and these water molecules, remember, they're still trying to escape out and become a gas, right? They're still trying to escape out, but some of them are being blocked, and they can't get to the gas phase because there are salt particles that are hanging out in their way. So that makes less solvent molecules will be able to escape into the liquid phase because they're being blocked, right? And the decrease, this decrease is proportional, the decrease is proportional to the number of solute particles that you actually have dissolved. Okay, so what in the world does that mean, Ms. Ruark? Well, let's make some sense of it. Let's look here. We have glucose, which is sugar, C6H12O6. We have sodium chloride, and we have calcium chloride. Okay, glucose is a covalent bond, right? It is a molecule. It does not break apart into ions when you put it in water because it's not made of ions. It's a molecule. Okay, so when we put glucose in water, when we put sugar in water, it doesn't dissolve and break apart into ions. It just dissolves into glucose molecules that are floating around in substance. Okay. Sodium chloride, however, when we put it in, it is ionic, and so it will break apart into the ions that make it up. And so we'd end up with sodium ions and chlorine ions floating around in solution. Well, here we have calcium chloride, and calcium chloride actually breaks up into calcium ions and chlorine ions. But look, we have 2 chlorines for every 1 calcium, so we would have to break it up and have 1 calcium and 2 chlorines floating around in solution. Okay, here we only have 1 thing when it drops in, so we'd only have 1. For every molecule that we put in, we have 1 molecule. Well, here, for every molecule that we put in, we have 2 substances that are affecting it. And on this one, for every 1 that we drop in, we have 3 substances that are affecting it. And so that's why glucose has the least impact on vapor pressure lowering, because there's only 1 thing there to block instead of 2. Okay, where there's 2 here. Well, guess what? Sodium chloride does a good job, but calcium chloride does an even better job. And that's because calcium chloride breaks up into 3 things. So instead of just having 2 things there, now we have a 3rd thing there that's just kind of in the way, and it's blocking it and keeping it from going further. Okay, and that's how vapor pressure lowering works. Let's see, vapor pressure is going to decrease when a non-volatile solute is added to a solvent. Non-volatile means if it's volatile, it does not like to stay in the liquid phase. It likes to go into the gaseous phase. So it's non-volatile. It's okay being a liquid. And so your vapor pressure is going to decrease when it's non-volatile. The reason for that is because if it's volatile, it's forcing. It wants to go to that gaseous phase. And so you're increasing the number of vapor molecules that you have. Right? And then vapor pressure lowering is directly proportional to a solution's concentration. Right? The more concentrated it is, the lower the vapor pressure because you have more things. You have more particles. There's more numbers in there. All right, boiling point. So boiling point will change. Boiling point will be elevated. So boiling point elevation, when a solute that dissociates, breaks apart, is added to a solution, the boiling point of the solution will increase. The boiling point is the temperature where the vapor pressure of the liquid is equal to the atmospheric pressure. So when the vapor pressure and the atmospheric pressure are equal, then a substance will be able to boil. We've already talked about this when we went through gas laws, so hopefully this is just a review. Okay, when solute is added, the vapor pressure is going to be lowered. We just said that in the previous little section. And when the vapor pressure is lower, the boiling point can be raised. And the boiling point can be raised because it doesn't have to reach a higher pressure in order to boil. Sorry. All right, and then additional energy or kinetic energy, energy of motion, additional kinetic energy is going to be needed to break apart the solute-solvent interactions, okay, or those attractions that are holding them together. And the temperature difference between the boiling point of a solution and the pure solvent depends on the amount or number of solute particles. That's like the 4th time we've heard that. Huh. Okay, some more stuff. Here is an equation that we can use for boiling point elevation, and it's delta Kb. Delta means the change in the boiling point temperature. Kb is a constant for the solvent. M is molality, and I is called the Van't Hoff factor, which I'll explain in just a moment. Okay, and this is going to occur because the additional solute particles will lower the vapor pressure, so more pressure is needed to boil. Okay, more energy is needed to break the bonds or the intermolecular forces that are holding those things together and exert an additional vapor pressure. All right, so what is I? Well, I is called the Van't Hoff factor, and it's just a fancy way of saying, or it's just a way that we use that says the number of particles into which the added solute will dissociate. Okay, dissociate means to break apart. All right, so for all molecular compounds, that means covalent. For all molecular compounds, the Van't Hoff factor is going to be equal to 1. It doesn't change because it's not going to break apart. For ionic compounds that are strong, meaning looking at your solubility rules, do they break apart completely? Are they soluble? The Van't Hoff factor is dependent upon the number of particles dissociating once it's dissolved. So some examples here, NaCl breaks up into Na and Cl. We would have a Van't Hoff factor of 2 because we have two things. We've already done this, right? Yes. All right, Na3PO4 breaks apart into 3 sodiums and 1 phosphate, so we would have a Van't Hoff factor of 4. Okay, freezing point depression. So how does this work? Well, the temperature difference between the freezing point of the solution and the pure solvent is our freezing point depression. The solute is going to disrupt the normal geometric pattern of a pure frozen solvent in a solution. So it's not going to be able to stay together in its nice, pretty lattice structure. It's going to break apart. Okay, additional kinetic energy must be lost for the solidification to occur. So the equation that we use is similar to the last equation I showed you, except now it's delta TF and KF instead of delta TB and KB. Okay, delta TF is just the change in the freezing point temperature. Kf is the constant for freezing point elevation, and a constant will always be given to you. And then delta T and delta TB can also be used to find the molar mass of a substance if we need to, and I might show you guys that. All right, so there's a table. This is an example of a type of constant table that you would see. We probably won't give it to you this way. I'll probably give it to you in the problem though. All right, so here it says a solution is prepared, example 1, by dissolving 4.9 grams of sucrose in 175 grams of water. Okay, this is our solute, and this is our solvent. Calculate the boiling point of this solution. Sucrose is a non-electrolyte. That means that it does not break apart, and that means that it is covalent, so it has an I factor of 1. Okay. Delta TB equals I times KB times molality is the equation that we're going to use. And so we need an I, we need a KB, and we need a molality. All right, so I we said is 1. KB is a number you get from your equation, from your chart. So here we look and we say water, its boiling point KB is 0.51. So our KB is 0.51. And it's degrees Celsius times kilograms over moles or negative molality. All right, and then our molality, we don't have that, but we can figure it out though, right? Because molality is equal to moles of solute over kilograms of solvent. We know that one. All right, so moles of solute. We have 4.9 grams of solute. So 4.9 grams of sucrose, and we just need to go from grams to moles. So 1 mole is equal to the formula mass, and I'm going to go ahead and put it for time's sake. So 342.34 grams, and that'll give us moles. And when we plug that into the calculator, it gives us 0.01431 moles. All right, we need to divide that by our kilograms of solvent. Here's our solvent, but we need it in kilograms, so 0.175 kilograms. 0.175 kilograms. Okay, if you're unsure how I did that, come see me in class and I'll tell you. All right, to get our molality, we divide one by the other, so we end up with 0.082 molality. And now we plug all these into our equation. We're going to solve for the change in boiling point, and that's equal to 1 for I. KB is 0.51 degrees Celsius times kilograms over moles. And then we multiply that by our molality, which is 0.082. Now molality is moles per kilogram, right? So I'm going to write moles per kilogram, but you can put M, your choice. Just like here, you could put inverse M, your choice. I do it this way so you can see our units cancel, moles cancel, we're left with degrees Celsius. So now 1 times 0.51 times 0.082, and that gives us 0.0417 degrees Celsius. But that's just the change in boiling point. We want the actual boiling point. Well, water boils at 100 degrees Celsius. So 100 plus 0.0417, and that equals 100.04, and we'll just leave it at that, and that's the new boiling point.